Hello, here we're going to look at 1.7, solving systems of inequalities by graphing. Here's the why. We looked at regular inequalities and constraints, but life often has more than one requirement at a time. So examples of that are speed limit. You don't want to go too fast, but you also don't want to go too slow. So there's two constraints. Making purchases, sometimes you need to buy certain things, but you want to make sure you don't buy too many of them, for either maybe spending too much or considering how much storage you might have to store the purchases. Grades, because sometimes if you're trying to keep maybe an A after the midterm exam, you have a window. You can score maybe between an 87 and a 100 to keep your grade. Or if you were, at a B and you wanted to just keep the B, you might need to score from a 78 to an 84 or something like that. So there's often two constraints. If we take a look at this picture, we can see what's going to be happening here for us when we are working with systems of inequalities. Because remember, systems means we're working with at least two pieces, so two inequalities or more. We can also have more than two. So this says label the boundary lines in the solution region for the systems of the inequalities shown. So if we look at this line, I can see that it's y, and if you're trying to think about, well, what's my inequality need to do? You can see that right here, this is our solution, right? Because it is the double shaded region. And if we look at that in relation to this line, it is above our line. So we're going to have a y is greater than or equal to. And then we could look at the slope, which I'll look at these 2 points here. So we have a slope of rise 3, run 1, so 3x with a y-intercept of -3. That's one of our inequalities right there. Now for this one, we have a y is less than or equal to, because that double shaded region is below our line. And for that, it has a slope of down 1 to the right 2, so we have a -1/2, and then a y-intercept of 3. So what we'll ultimately be doing here is graphing two or more inequalities and figuring out the double shaded region. And you'll also have a single shaded region. Like right here is a single shaded region, right here is a single shaded region, and those will come about too. But our solution, so anywhere in that double shaded region, if I pick a coordinate point, so let me just pick one right here. I'm going to pick -3, 0. And if I plug that into both inequalities, you'll see that I get a true statement. And I'm missing an x right there, so let's toss that x in there. And if I go through and evaluate both of these, we get that 0, so here's a -9 minus 3. 0 is greater than or equal to -12. When I evaluate this one, we get a 3/2 plus 3. And I'll go ahead and just think of 3/2 as 1.5. 1.5 plus 3 is 4.5. We get that 0 is less than or equal to 4.5. So if I pick any coordinate point out of the double shaded region, it's going to make both inequalities true at the same time. And that's the only region that would do that. If I pick one from the single shaded region, it would make one of the equations work. If I pick a point from this other shaded region, it would make the other equation work. But if I pick a point from the non-shaded region, it wouldn't work for either one of the inequalities. So here's the difference between solving a system of equations by graphing and solving systems and inequalities by graphing. So if we make this side equations and this side inequalities, here we have graph both lines, right? And for this one, we're going to graph both inequalities Now on this one, you have to remember that that will involve doing the shadings. But there is no shadings when you're graphing equations. For the solution, for systems of equations, you find the intersection point. Which was if we had two lines, the solution was the point where they crossed over. But for systems of inequalities, you need to identify the double shaded region. The intersection point isn't as useful. It still might be something you need to answer a question, but we can see over here in this graph we didn't care about the intersection point, which was right here, because that's just one point that works. And with systems of inequalities, we're not just concerned about one exact spot, but rather a shaded picture of all of the points that will work. Some scenarios that this can help us take down would be something like this. The auditorium at McCaskey East High School in Lancaster, Pennsylvania has 800 seats. Suppose that the drama club has a goal of making $3,400 each night of their spring play to cover expenses and raise money for the club. Adult tickets are $7 and student/senior tickets are $4. So what we're going to do is make a graph and figure out all the different combinations that would meet two requirements. We want to make sure that there's no more than 800 people seated, and we want to make sure that we make at least 3,400. And there is going to be multiple options for that to happen, but there's going to be some combinations that don't work for both of those. And the graph that we'll make together will help us identify what those solutions are. As for the rest of this, we'll complete it together.